Second speaker is Peter Paule from Johannes Kepler University. His talk title is Holonomic Functions, Modular Forms, Algorithmic Snapshots. Please, Peter.
Thank you. Can you hear me?
Yes.
Thank you. So thanks also to the organizers, in particular to Tawfiq Mansour, who is the fundamental and energetic spirit behind all this. In my presentation, I would like to connect two different worlds, the universe of holonomic functions and that of modular forms. As I said, this will be an algorithmic connection, and let me start with the holonomic side, and let me start reading a quote. Thomas Kuhn famously believed that science is paradigm-based. His approach to science could be thus dubbed the paradigm. Doron Seilberger believes that mathematics in the future will be ansatz-based. So my approach to mathematical research could be called the ansatz. So actually, I could have asked Doron, are you still here? So I could have asked Doron.
Yes, thank you for quoting me. Thank you.
To read this, so this is quoting Doron, the part one of his great holonomic ansatz paper. And what I'm discussing here is again an ansatz, and it's strongly connected to that what Doron is saying here. So he continues his paper by saying what his favorite ansatz is. He defines holonomic sequences. He mentioned it already in his talk a couple of minutes ago, because Stanley, so he used the word p-recursive. This is Stanley's notation, Stanley's wording or terminology. A sequence, I call it holonomic because I also use holonomic function. I find this convenient that using the same word for two sides of the same medal. So a sequence is called holonomic if it satisfies a linear recurrence relation with polynomial coefficients. So Doron here points to Stanley's pioneering paper that you see cited here. So Stanley calls it, as I said, p-recursive instead of holonomic. Doron continues to cite, he says, in my seminal paper, but it's really a breakthrough paper, he shows that almost everything in sight in enumerative combinatorics and a lot elsewhere is holonomic. And so this is one feature, the ubiquitous occurrence of holonomic sequences and functions. I also will discuss functions. And another important ingredient I take from Doron here, I continue the quote, is the guess and proof approach. So Doron takes as a starting problem, the problem of finding a formula for the number of ways of walking into the positive quadrant of the 2D square lattice from the origin to the point Mn using fundamental steps. So this is north and steps to the east. He explains that by obvious combinatorics, you obtain a recurrence, subject to boundary conditions. Then in the next step, you guess a closed form for the solution of this recurrence. And then you prove. The verification is just zero recognition of rational functions. In this talk, I also use a guess and proof approach. The difference here is we guess the holonomic recurrence. So we first will guess a holonomic recurrence. This means linear with polynomial coefficients. And then we prove the validity of this recurrence. And we prove it by converting it to a differential equation. So the differential equation refers now to the notion of holonomic function. A function, look at the expansion, assume it's analytic around zero, or take a formal power series with the coefficient sequence Cn that is holonomic. And if you look at the function, it satisfies a differential equation that I also call holonomic. Stanley would call it D-finite. This means linear differential equation with polynomial coefficient. This relation can also be read backwards. You start with a holonomic function object. Then you can prove that the coefficient sequence in the Taylor expansion gives you a holonomic sequence. The ansatz, so the differential equation in this talk is always a holonomic differential equation, linear with polynomial coefficients. The ansatz in this talk is this. You fix two functions. I will explain briefly, not in detail, what modular forms are, but the G on the left of this relation at the bottom is a modular form of weight K. We take a modular form of weight 0 that is also called modular function. This is with respect to some subgroup of the special linear group. It sounds old fancy, but it's very concrete in a couple of minutes. What we want to do is we want to find an expansion of this type. So we want to expand the G in powers in terms of a power sum in H, and we want to find the corresponding coefficients. So this is the first introduction to the holonomic side. Now the modular form side. Again, I quote, the unreasonable effectiveness of classical modular forms is that each modular form has calculable invariance. So you calculate some numbers like weight level. It's not really relevant what the meaning of this is. And the first number of its Fourier expansion, this is the expansion in terms of a power series, then this suffices to characterize such a series or such a function uniquely. In other words, so I'm quoting, actually I should reveal whom I'm quoting. I'm quoting Don Sagier here in the survey paper on Mach theta functions. So he takes as examples on the left-hand side, it's in a fancy way written the Euler Pentagonal number theorem. On the right-hand side, you see the famous theorem due to Jacobi. And let's have a closer look at the ingredients of these things. So in the Euler Pentagonal number theorem, you see the Q product 1 minus Q to the J. Here I put a little Q to a Q to a little power of 1 divided by 24 in front, because I want to relate really two functions. The relation is only in a certain step. After relating generating functions to analytic functions, I again do the proving on purely algebraic grounds, as you will see. But for understanding what's behind, I need to consider the Dedekind eta function also as a function in tau. The tau is here living in the upper half plane. And the Q makes the mapping from the upper half complex plane to the open unique disk. This is, so to say, for those who want to understand the analytic connection between these two types of presentations. The Jacobi theta functions, Sagier wrote it in terms of Q, which would be the x squared here. For the algorithmic proving, it's convenient to use as Fourier variable the e to the pi I tau, so this is Q1 half. And the ingredients involved here is on the right-hand side, the theta function, the Jacobi theta function with index 3 to the 4th power. There is the Jacobi with index 2 to the 4th power on the left-hand side, the second member here. And I need both of these objects to define what is called the modular lambda function. You take the quotients of these two guys, and in the X expansion, so all these objects, you can think of all these objects as a power series, either in X or in Q. The modularity comes in when you view this object as a function in tau. So if you do a Möbius transformation on the argument, you can use matrices to this end. So here in the first line, I use an integer matrix A, B, C, D. SL2 means, so 2 times 2, special linear group means the determinant should be 1. So if I do this transformation on the argument of the eta, and if you raise this to the 24th power, you return the original eta to the 24th power times what is called in fancy language automorphic factor in front. What counts here is, but it's not really relevant for the mechanism of what I'm going to explain you, the algorithmic mechanism. There is the 12. The 12 of the linear automorphic factor is called the weight. So the Dedekind eta raised to the 24th power, also called the discriminant, the modular discriminant, has weight 12. The other objects that we have seen previously, the theta 2 and the theta 3 squared, have the power of the automorphic factor is 1, and the transformations are now with respect to subgroups of the special linear group. How this is defined is not really relevant here. The modular form, that this is relevant to some extent, is an object of weight 0. So you see that if you transform the modular lambda function with respect to a certain subgroup of the SL2, the automorphic factor disappears completely. So the weight, alternatively, you can express this putting the weight to 0. So this is the setting. And I said at the beginning that this is a completely different universe. So I'm tempted to call modular forms even anti-holonomic functions, because they do not satisfy holonomic differential equations. They are quite a way off from the linearity of differential equations. They satisfy a nonlinear, this is a general statement that you can prove, a nonlinear differential equation of order 3 with constant coefficients. So this is different universes. Still, there is an important connection between these two. And these connections I will call further on holonomic relations. So recall, this is our ansatz, given a modular form G, a modular form H of weight 0, and we want to expand the G in terms of powers of H. This means we want to find the corresponding coefficients. The guess and then proof procedure is explained in this paper, and I explained it here in this talk according a concrete example. Take as the G the Jacobi theta 3 squared. Take as the H this polynomial in the modular lambda function. The 1/16 is for the sake of normalization, but since the lambda is a modular function, you can form a polynomial of this lambda. It's still a modular function, so this is a choice that will give you something nice, as you will see on the next slides. But you also can choose other polynomial expressions in terms of the lambda. For computations, we use the expansions in terms of powers of x. If x is the variable to use here, it can be also the q. The q, I'm recalling, would be the x squared, so the e to the 2 pi I tau. But this is a technicality. Here, in this talk, we either use x or we use x squared, which is equal to q. So recalling the task, find an expansion of the given G in this way. So here I replace the definition of lambda by the quotient of 2 thetas, and the 2 thetas again, this quotient is a power series in x. This is what I said. So the thetas are modular forms of weight 1. If you do the quotient, it's giving you a modular function of weight 0. This means a modular function, and the lambda, which is then, it's stated here, the lambda. Now I do computations. To do the guessing part, we use something that has been implemented by Christian Mallinger years ago. We plug in the theta, the definition of the theta 3. We use the mathematical internal definition. You don't need to do it for sake of complexity. Sometimes it's preferable to you do it your own way or use a product representation. But it's not the theme here. For the purpose of demonstration, it's more than sufficient to use the built-in definition. And we do it in this way that the G at n, capital N here, gives you the series expansion up to order 10. So if I would say G20, I would get the expansion up to x to the 20. Same with the theta 2. We use the Mathematica built-in elliptic theta definition. We produce the lambda as the quotient of these 2 thetas. So if we want to now to see the H with order expanded up to order 10, this what you see at the bottom of the screen is just the truncated Taylor series of the H expansion. What we need for the guessing is an initial string of values of the Cn. So Doron in his talk referred to this business. You compute sufficiently many values where you then continue your holonomic business on. In order to get the Cn here, from the original relation, we have the G expressed as a power series in H. So if we take the compositorial inverse of the H, we get the C's explicitly, at least an initial string of the C's explicitly. This is done in one line by this comment. So we get the C0 is 1, the C1 is 4, the C2 is 100, the C3 is 3,600, etc. So we put these C's together into a list. We don't need thousands of them. We just need 1, 2, 3, 4, 5, 6, 7, 8, 9 values for the C's. And then we do a guessing. We guess a recurrence. We try to guess a recurrence for the C's. This is done in Mallinger's package with this procedure call. Executing it gives you the C's, the recurrence of order 1 for the C's. It's a holonomic recurrence for the C's. So we guessed, this is just echoing the bottom expression from the previous page. We guessed an order 1 recurrence. Next, as I said, we do the proving using differential equation. So we convert, we now use this connection, coefficient sequence holonomic gives you a holonomic differential equation for the generating function. So this is also done by Mallinger's package in this way. And you see the generating function for the guessed, the C's are guessed in this way to satisfy this recurrence of order 1. And this is transformed into a guessed differential equation for the y in question. So summarizing, for the relation G is equal to y at h, y being a holonomic power series, we either have the description of the coefficients in terms of a holonomic recurrence or of the generating function in terms of a holonomic differential equation. And still, this is a guess. What we now want to do in this context is we want to prove that the Cn indeed satisfies this recurrence, and we do it by proving that the corresponding differential equation is a holonomic, one satisfying the required relation. Before we do this, let us have a look at existence. You can guarantee existence. It's not even too hard to prove this. You can prove existence of holonomic coefficient sequence for any G and H in our ansatz. So this means for any modular form G and for any modular function H we choose with respect to a certain subgroup, modularity with respect to a certain subgroup of the special linear group, we can guarantee that the connection between G and H, powers of H, is made up by a holonomic function, or by, if you like, a holonomic power series. So the Cn's are in all our ansatz pairs are guaranteed to be holonomic. I should mention that Sagier, in a very widely distributed survey paper in the book 1, 2, 3 of modular forms, he restricts existence of modularity of holonomicity of the Cn's to certain constraints. So he requires that the underlying Riemann surface for the subgroup, it's not relevant for this talk, but I want to mention it. He restricts it to genus 0 of the underlying Riemann surface for the modular subgroup, for the level subgroup. And also, as a second requirement, he needs that the H has order 1, being, in other words, in this modular form terminology, being a Hauptmodul for the corresponding modular function space.
Peter, sorry.
Sure.
Fact, is it due to Sagier, the existence of holonomic?
No, this is I send you the reference. I don't want to pronounce the name incorrectly, but there's a classic paper where it's proved. It's like Slater Splitter. Maybe someone in the audience knows. I send you the reference. But Sagier restricts. Sagier restricts, and also this guy. They restrict to these are strong requirements: genus 0 and order 1 for the H. And Radu observed that this restriction can be dropped entirely. So this gives a fantastic extra flexibility in this ansatz.
Thank you. Another quick question. I took the liberty of going to OIS. The sequence you had before, 1, 4, 100, 3600, is in OIS A12777.
Yes.
It's related?
You will see.
Okay, thank you.
I continue the example. And you will see the relevance, and it's in the database because it's it's relevant for sum of squares and sorts of these.
Thank you.
So back to Zage, this relation he calls is the heart of the original discovery of modular forms by Gauss, and later the work of Fricke and Klein and others. Now it's relating to Picard-Fuchs differential equations, also to fancy things like Gauss-Manning connection. But as Zage underlines, it's not nearly as well known as it ought to be. And a goal of the talk is to get you interested in this business. I said to Doron, I am continuing the example. So what we did so far, Doron mentioned the expansion of the theta-3 squared in Sloan's database. So we will see why this is relevant, why this is a relevant entry in Sloan's database. So what we guessed so far is that the expansion that we are after is this form. If you like hypergeometric notation, the 2F1 notation, which simply comes from converting the order 1 recurrence for the Cn into closed form. You use, as you see here, you use rising factorial. This means 1 divided by 4 times 1 divided by 4 plus 1 is the next factor. You go up to n factors. And this 1, 4 goes into this hypergeometric notation. This 1, 4 goes to the second entry. This 1 goes to the bottom entry. This is the corresponding argument, which corresponds to this lambda. And this 1 over 16 is swallowed by this 64 to the nth power. So this is what we guessed so far. Now we want to prove it. So this is recalling our ansatz. And I said, in order, so we guessed the differential equation. How can we prove this differential equation? So the proving is now done in this way. Sorry to jump back. This is on the generating function level. Here you see the argument is the x. For Doron might not like this jump, but for a moment, we jump to analysis. We plug in the h tau, because so we can do this because it has order 1 or it has higher order, as Radu has shown, does not matter. But it needs to be consistent with convergence at 0. So we can guarantee this convergence by taking the imaginary part of tau sufficiently large. And now our goal is to prove this the correctness of this differential equation. Namely, why are we moving to the differential equation? We need to plug in what we know about the setting. We know there's a unique y doing this job, and the chain rule now gives us all what we need elsewhere. Namely, for instance, so the y is expressed in terms of the g. This y in h is expressed as a rational function derivatives of the j and the h that we have in hands. It's just expressed in terms of power series in x. The second derivative of y in h is a rational function in derivatives of h and g again. And this works also in general, not only in this example. So what we can do now is we can rephrase this. And now we leave analysis already. We can rephrase this in terms of relations that only involves derivatives of the g and h, only power series arithmetics. Still, we need to do it systematically. We rewrite this relation in terms of a relation. So we use a 1 here. We use this rational function. We use this rational function that we borrow from Yi van Yang, and prove that these Yang functions are linearly independent. So proving the correctness of differential equation amounts to proving, to showing that these coefficients that are also power series in x are actually 0. This is actually what I said. The derivatives of a power series in x are also power series in x because of this relation. The coefficients, well, I did not say it explicitly. The coefficients are in the modular function field. They are very nice functions. The weight is 0. This is what I mean by nice. So the 0 recognition is even more easy to handle than in the case of modular forms. I'm referring back to the quote of Don Zage. So what we did in the paper is to prove, so use these Yang functions as a basis to prove their linear independence. This is, so to say, standard manipulatorics. And the rest is to prove that the modular function coefficients are 0, which can be proved again fully algebraically by supplying corresponding bounds, up to which we compute the expansion in powers of x or in powers of q. If this, for instance, if the given bound is 10, we compute the first 11 coefficients that guarantees us, if they are 0, that the whole object continues to have 0 coefficients. This is spelled out, so we called our algorithm mod forms DE. This is spelled out in the paper that appeared in the proceedings of the conference in Transylvania. And I finish. I used the remaining 5 minutes of my talk for showing you very quickly, kind of in an animation applications. There are famous series Ramanujan gave for 1 over pi. We start with that what we have found and proved finally with this algorithm. If you are in hypergeometrics, you know that this 2f1 can be transformed to this form. Why I'm doing this? Because then the original theta 3 squared can be expressed in this way. I can do this independently of classic hypergeometrics. I can use to prove this, and to find this, I can use the method I explained previously by guess and proof approach. Why did I do the transformation? I want to relate to classic mathematics, to the complete elliptic integral. And the story goes like this. The Borweins use this identity and 11 similar ones to explain 17 formulas Ramanujan gave to approximate 1 over pi. Now, all these identities that were used by Borweins and proved first by the Borweins can be proved and also found automatically with the mod form algorithm that I was explaining you in a very sketchy way. One of the most stunning applications in this regard happened in 1985, where Bill Gosper computed 7.5 million digits of pi using this formula of Ramanujan, which fits exactly into this domain. So quoting Barua, Berndt, and Chan, there was only one problem with Gosper's calculation. This key identity has not yet been proved. So it was taken from Ramanujan, but there was no proof there. Now with this approach that I showed you, you can prove this. This is what the Borweins proved. But starting with this elliptic integral, you can even discover this prefactor. You can discover this relation underlying this key identity. Further applications to finish up. Xavier mentioned Fricke and Klein. So what they were interested in inverting. This is compositorial inversion. This is multiplicative inversion of the Klein J function. But among other things, they wanted to expand the Eisenstein E4 in terms of the inverse of the J function. Here are the definitions. Sorry, I have to jump over this. Just keep in mind, this is a classic relation Fricke and Klein were after. With this guess and proof approach, you first compute these coefficients, the C's. Then you guess a recurrence. You get this recurrence. It's of order 2. You can try to find a binomial sum representation. There are now algorithms by Petkov, Scheck, and Antonio Pastor. Since the E4 has weight 4, you might speculate, is there a better relation if you take the 4th root of it? Indeed it is. You find this nice hypergeometric representation. You also can play similar things with the 2nd root, which relates to the theory of holonomic differential equation. So for instance, this identity is related to something that arises in the context of Calabi-Yau. And 2 more examples. There is Boyka's alternative proof to the branches of the irrationality of zeta 3. Boyka's used a modular relation, as I would call it. He used for the G, he used this. For the H, he used this. And with our approach, we just guess a recurrence for the CK. We guess the recurrence for the CK. Somehow I killed this. Here it is, sorry. We find this relation of order 2, and Doron immediately recognizes that this is the Apari recurrence that in some presentation can be spelled out in this form. So the Zeilberger algorithm would give you back this relation that you obtain directly from the approach, from this setting, from these answers that I described to you. And I want to finish with a slight deviation from the main track of this talk, relating this strategy to partitions. So take a holonomic sequence defined in this way. So it's a 4-term recurrence where the jump between the parts in steps 2. Take this bunch of initial conditions. Theorem. It turns out that this sequence, the CK, are integers, not quite, divided by powers of 2. This is what is spelled out here. And in addition, all these integers in the numerator are divisible by 11. And what's behind is a holonomic relation of the type we considered. Here the difference is that G is a modular form of weight 0. It involves partition numbers that are famous if you are in Q series. And the 11 divisibility that I showed you here comes from the corresponding, and here the deviation from the previous theme is not differential equations, but we have now algebraic relations between the objects in question that also can be guessed and then proved computationally. And the 11 divisibility feature is a consequence of a famous theorem that originally was first observed by Ramanujan, but it immediately comes from this algebraic relation, because you see the G coefficients have to be divisible by 11 and 11 because of this setting. So this concludes my talk. Actually, I skipped the conclusion. I think I'm over time already. Thank you for your attention.
Thank you very much, Peter, for this very nice talk. Any questions, please?
Yeah, a quick comment. So you have a completely computer generated from scratch reproof of the Ramanujan congruences in mod 11 and 7 and 5?
We have other proofs. This proof is, you are right, but here I stick in lots of knowledge. So this context needs to be explored further. But for instance, Radu has an algorithmic approach that does what you said, really automatic, without inserting knowledge. What I insert here, Doran, the difference is I need to start with a G and an H.
Thank you. Very interesting.
And here you need to stick in knowledge, whereas in Radu's approach you don't.
Thank you. And another thing, so you now have automatic proof of many of the Bauwein and Bauwein.
That's true. That's true.
That's beautiful. Thank you.
That's true.
Thank you. Any other questions, comments?
Yes, Peter. This is Bill.
Hi, Bill.
One simple question. The recurrences you guessed, were they known elsewhere?
Those I showed you were known, but we have examples where they are new.
Okay.
We have examples for choices of G and H that produces new, but this is still open for further explorations. We just started this business, and it's plenty of space to move here.
Thank you.
Thank you. Any further questions? So in the solution of this free packing problem for dimension 8 and 24, I guess they also use these modular forms, right, in their solution for this problem?
Which proof are you? Sphere packing?
Yes, free packing problem for dimension.
The fifth medal for Marina.
Yeah.
I did not check what she is using. They used definitely they used modular forms. I cannot say anything whether they used relations of this type, but what I can say is that in many work where modular forms occur, this holonomic bridge is actually either lurking behind the scene or is explicitly there.
Okay, so I just wanted to ask if they use similar approach here or.
I don't know.
Yeah, okay.
They use modular forms.
Yeah. Okay. Any further questions, please? Comments? Okay, so thank you, Paul. Peter, again, it was a wonderful talk. So for
Thank you.